Welcome to the third lecture of the fourth day of the PETS module. We'll continue our discussion around databases, and our topic now is differential privacy. Differential privacy is about releasing data, especially from a particular type of database, the so-called statistical databases. Statistical databases differ from regular databases from the following property. They release statistical information about the contents of that database or the subjects in this database. So, for instance, if I have a database of salaries of people living in a certain region, I can get the average of the salaries and the deviation of the salary, but not the particular salary information about an individual. So that a statistical database will not give to me. So, for instance, if you look at data release, it will not give much information about individuals. And that's the objective of a statistical database. Of course, such databases also have their own privacy risks in a special form. So if you look at this example that I have here, I have two different data sets, one with Alice and the other one without Alice. And if I query those two databases for the, let's say, average salary, then one will come with the added information of Alice and the other one without the information from Alice. And that creates a problem, because if you are a smarter attacker or a smarter adversary, we just need to compare the two outputs or the two responses to my queries and figure out that the difference corresponds to Alice. If I know, or if I would know that Alice will be one at the databases, but not on the other. And that's the type of problem that differential privacy aims at solve, or at least aims at addressing. So differential privacy, or the idea behind it, is to quantify the difference in what might be learned about an individual, or let's say Alice, from a database that has Alice and another one that doesn't have Alice. If you look again at those two databases that had before, D and D prime, so the difference should be bounded by a risk factor that's called epsilon. And that's what differential privacy does. He bounds this risk to a factor. So when you do two queries to these two different databases, one with Alice and another one without Alice, a maximum amount of information is released. So one can only learn a factor information. So what you're measuring here is to which extent can anyone, for instance, can Alice blend into the crowd? And also a measure of plausible deniability of the claim that I'm not even on the database. So one database that has Alice, another one that doesn't have Alice, will not give enough information. If you look from an attacker point of view, what this definition that I just gave to you means is that an attacker, Eve, will not be able to learn any additional information that she could not learn if the participant had opted out. It means Eve will not learn anything, or there will be no additional information for Eve, if Alice will be in the database or Alice will not be in the database. And that difference will be bounded by epsilon. The formalization of this difference is basically what you learn from the first query that has Alice in that, and from another query that doesn't have Alice in that is less or equal to the exponentiation of epsilon, where if the exponentiation of epsilon equal 1, it means that the information that we receive from query and query prime is the same, then Alice has absolute no effect on the database. Of course, the effect of that is that also Alice has absolute zero utility on the data, which might be a problem. The problem that we have here is if every subject that's part of the data set adds zero utility to the data set, by definition have a data set that has absolute zero utility. So a zero utility in a data set also or from all subjects also means a zero utility from the data. So we learn nothing by querying that. What's bad from the point of view of data sets, or the utility of having a database like this. But that's why we have to learn how to control epsilon. But let's see how actually we implement differential privacy. And how you do that? The basic idea is to add noise to the query result. And how you do that? It basically depends on the mechanism design and the type of data that you have there. So for instance, if you talk about categorical data, there are so-called exponential mechanisms that we're going to use. For other numerical data, there's the Laplace mechanism that we're going to use. Both of those methods will work by adding noise. But simply adding noise does not offer a good solution. Imagine that, on a previous example, that Eve could have queried our database as many times as she'd like. It would mean that by obtaining as many results as she'd like, she could cancel the noise that you're adding to our data set and finding out what will be the information for Alice. Therefore, we need a better solution than just adding random noise. And for that, differential privacy has the concept of a privacy budget. The privacy budget will define a limit for you, a limit on how many queries you can ask this database, and also for each query, what should be the maximum amount of the epsilon that this database is going to leak. So how much personal data actually is leaked per query. And the sum of the data leak of all those queries, it will be your privacy budget. Differential privacy offers you a rigorous framework when releasing data and offers these theoretical bounds of how much personal data one attacker can obtain when querying the database. Also, differential privacy is deployed in the wild. Implementation of differential privacy were also deployed by large companies such as Apple, which has it in its operational systems since macOS Sierra and iOS 10. When collecting data from the iPhone platform, Apple used different values for epsilon, from 2 to 8, depending which category of data it's looking at. For instance, for emojis, Apple uses a privacy budget with epsilon of 4 and submits 1 donation per day. For other types of data, for instance for health types, Apple uses a privacy budget with epsilon of 2 and limits the contribution also to 1 donation a day. For some categories, like lookup hints, the contributions are 2 per day and the budget of epsilon is 4. Another big company, Uber, releases open source tools that implement differential privacy. So you might look at them at this address that I provide here in this slide. Differential privacy has nevertheless some limitations. A database that implements differential privacy does not mean that Eve learns nothing about Alice when querying for results. Differential privacy also don't take into account background information about the dataset or other datasets that exist on the side. In addition, datasets that have way too small privacy budgets when queried offer no data utility. It means that every time that you query this database, only trash will come out. So there will be no utility for the data that you obtain. So setting the value of epsilon actually defines for you how much privacy is enough for you. And there's no rule of thumb on how to set those budgets. That's something that you and your lawyer are going to be defined together. So now we reach the end of part 4 on database privacy. In this part, we learn why do you need database privacy, k-anonymity, and also this lecture on differential privacy. On the next part, we're going to look into additional topics around privacy-enhancing technologies, especially blockchains, anonymous credential, and transparency-enhancing technologies, or TETs. Thank you for today, and see you next time.